The first question asks us to refer to tab 2 to determine which sections of the cooling curve would be present on the graph based on the experiment that was described. So the experiment that was described was determining the freezing point. So we would have to start as a liquid with this substance and then cool it until it became a solid past the freezing point. So on our cooling curve, we're going to need to include the segment for where freezing is happening, where it's a liquid, and where it's a solid. So that's going to be segments 3, 4, and 5 on the cooling curve. The next question again refers to tab 2. Which of the following errors would give us a freezing point that is too high? So the first choice is the thermometer is sitting on the bottom of the test tube instead of suspended in the middle of the sample. So where the thermometer is touching the glass, it's a little bit cooler as the sample is being cooled from the outside to the inside. So the thermometer is going to be measuring a temperature that's a little bit too low, so this would decrease our freezing temperature. The sample not being stirred during data collection. The coldest part of the sample is the part that's freezing. So that would freeze around the probe or thermometer, and this would again give us a lower freezing temperature. So that answer can't be correct either. It's really hot in the lab, and the temperature was higher than normal. The freezing point of a substance is a constant. It doesn't matter how hot the lab is unless the lab is warmer than the freezing temperature. But this is a constant. It has nothing to do with the temperature inside the lab. So this has no effect on freezing temperature. So this answer can't be correct either. The last choice is choice D. The student was holding the temperature probe by the metal piece instead of by the cord. So the temperature probe measures along the length of the metal probe. So if you're holding that with your hand, that probe is going to absorb some heat from your hand, and that's going to drive up the measured temperature. So this error could possibly give us a freezing point that is too high. The next question is referring to tab 1, so which can be concluded from the data that was collected. So there's several choices here that are about the molecular structure being complex. So what we mean by complexity has to do with there being more bonds in the molecule. If you have more bonds, this means that there's going to be a higher bond enthalpy, because when you break those bonds, you're talking about a greater amount of energy that has to be absorbed in order to do that because there's more bonds. So higher bond enthalpy leads to a higher enthalpy of combustion. So we can infer from the enthalpy of combustion how complex the molecule is. So the first choice says that corn oil is more complex than canola oil. So comparing these two enthalpy of combustions, we see that the corn oil is higher. So that does make sense that it would be more complex. So choice A certainly works. Let's look at choice B. Canola oil is less complex. So that doesn't match up because olive oil has a lower enthalpy of combustion. So that answer is not going to work. The article is correct in assuming that fresh and used soybean oil have the same molecular structure. That doesn't seem to be what the data is indicating, because the data is telling me they have different enthalpy of combustion, which means that there's different bonds that are being broken. And then the last one, molecular structure cannot be inferred from the data. That doesn't make any sense because this whole question is just about bond complexity and how that relates to enthalpy of combustion. Next question says to refer to tab 3. How much energy would I need to take 10 grams of liquid propane into a gas if the initial temperature is at negative 75 degrees Celsius? So on our heating curve, we've got the boiling point and the melting point, and we're starting at negative 75. So we need to heat the sample from negative 75 to the boiling point, which is 42.05, calculate that amount of heat. Then we have to calculate how much heat do we need to actually boil it and change it from liquid to gas. So we're going to do kind of two steps here. First, we're going to calculate the heat that I need to warm up the liquid, and then I'm going to calculate how much heat I would need to actually boil the liquid into a gas. So first, we're going to raise the temperature from -75 to the boiling point. So because I have a temperature change here, I can use Q equals mc delta T, the mass of the propane, the specific heat of liquid propane, and the temperature change for the propane. So we're ending at -42.05 and starting at -75, which means our delta T, our temperature, is increasing by 32.95. So I'm going to use this along with the mass of the propane and the specific heat of liquid propane to calculate the amount of heat. So here's the number that I get to go from a liquid at -75 to a liquid at 42.05 for propane. Now we're at the boiling point, so we want to change state from liquid to gas. So here there's no temperature change. So instead of using Q equals mc delta T, we got to use the heat of vaporization because that's the phase change that's happening. We're going from a liquid to a gas. So I'm going to start with the 10 grams of propane and convert that into moles of propane. The molar mass is given in tab 3, so that's very easy. We also have the heat of combustion at 16.258 kilojoules per mole. So I'm going to convert 10 grams into moles and then use heat of vaporization to convert this into kilojoules. Now my first answer was in joules, so I'm also going to do one more step just to convert kilojoules into joules. Now I just need to add these numbers together in order to get my answer. So I'm going to add what we needed for segment 1 plus what we did for segment 2. And when I combine that together, this is the answer that I get. Unfortunately, that's not one of the answer choices, so we had a typo here. But this is the correct way to do the problem. We have to figure out which segments of the heating curve we need to calculate heat for. Number 5 says to refer to tab 2, which is again the cooling curve. What energy changes are taking place at each segment of the graph? So this is a select all that applies, so there's going to be at least more than one correct answer for this. So you have to understand that kinetic energy is the energy of motion, and it depends on temperature. So kinetic energy is going to be changing anytime temperature is changing. So that's segments 1, 3, and 5. You also have to understand that potential energy has to do with the arrangement of particles, and this changes during a phase change. So that's going to be segments 2 and 4 here. So we're starting off as a gas, and that gas gets condensed into a liquid. So the arrangement of these particles is quite different, so their potential energy has also changed. During segment 4, we go from a liquid to a solid. So once again, the arrangement of those particles is changing during the flat segment, which means potential energy is changing. So kinetic energy here is going to decrease because this is a cooling curve. So right away, we can get rid of answer choices that mention increasing because we're decreasing in temperature. So kinetic and potential energy are going to be decreasing because we're going from a gas to a solid. Potential energy is going to be decreasing during the phase change. So kinetic energy decreases during segments 1, 3, and 5, and potential energy decreases during segments 2 and 4. So anytime kinetic energy is changing, potential energy is constant and vice versa. So option A we can get rid of because it says increasing. Option B we can get rid of. Choice C says kinetic energy is decreasing at 2 and 4. That's not accurate. It's potential. So then D makes sense. Potential energy is decreasing at 2 and 4. E makes sense. Kinetic energy is decreasing at 1, 3, and 5. F doesn't work because the potential energy is constant during 1, 3, and 5. And then the last choice here is another increasing option. So the correct choices are D and E. The next question asks you to refer to several tabs and then to draw and label an enthalpy diagram for the combustion of gaseous propane. So first and foremost, we've got combustion. So right away, we know that this is going to be an exothermic enthalpy diagram. So here's an exothermic enthalpy diagram. The reactants start with higher energy than the products, so the potential energy decreases during the course of the reaction. So I'm going to put my reactants, which was the propane and the 5 oxygens, and my products, which was 3 carbon dioxide and 4 water. And I'm going to put some lines on here just to represent the energy changes during this reaction. So we know that in order to break the bonds of the reactants, that's going to be endothermic. And then to form bonds for products, that's going to be exothermic. And the difference between those two values is our delta H. And since the exothermic piece is bigger than the endothermic piece, we know this is exothermic. But we can actually take this a step further. We can actually assign values to these energy changes. So we're going to need to draw a Lewis diagram for propane and oxygen and carbon dioxide and water. So I've just taken the reaction that we're given and I've just drawn out Lewis structures. And I need this because I need to see the bonds. One of the things that you were given was bond enthalpies. So you can use bond enthalpy to assign values to these energy changes. So first, breaking bonds is endothermic. So on the reactant side, I'm going to break carbon to hydrogen bonds, carbon to carbon bonds, and oxygen to oxygen double bonds. So 8 carbon to hydrogen bonds, and using the bond enthalpy is 413. So I'm going to multiply that. There's 2 carbon to carbon bonds, going to multiply that together. And then there's oxygen to oxygen double bond, but there's a 5 in front of that. So that means there's 5 oxygen to oxygen double bonds. The bond enthalpy for that is 495. So be careful. Make sure that you pick oxygen to oxygen double bond and not oxygen to oxygen single bond. So this can be all totaled up, and that gives me 6,475 kilojoules. I'm going to stick a positive sign on that because we're breaking these bonds, which is endothermic. Now I need to do the same thing on the other side. This is where we're going to be forming bonds on the product side. So we've got oxygen to carbon double bonds, and we've got hydrogen to oxygen single bonds. So in the carbon dioxide molecule, there's 2 carbon to oxygen double bonds, but we've got a 3 in front of that, so that's indicating 6 total moles of oxygen to carbon double bonds. I can look up the bond enthalpy from the chart. And we've got hydrogen to oxygen. There's 2 of them in each water molecule, but there's a 4 in front. So we're talking about 8 moles of bonds here. Multiply that by the bond enthalpy for hydrogen to oxygen single bond. And I can total that up and I get 8,498 kilojoules. And I'm going to stick a negative sign on this because bond forming is exothermic. So I need a negative number. So now I can fill in the amount of activation energy required and the amount of energy that is released during the course of reaction. And so the difference between them, if I combine these 2 numbers, I get negative 2,023 kilojoules. So that's my delta H. It's a negative number. And again, this is a combustion reaction, which is going to be exothermic. The next question says to refer to tab 5. Which of the following scenarios would release the most heat? So we've got 4 different reactions here, and I've just reproduced them on the screen. And we're starting out with different amounts of sodium hydroxide. So the heat of neutralization is given in kilojoules per mole. So that means that I can convert from moles to kilojoules using the heat of neutralization. So if all of these answer choices were in moles, this would just be a 1-step problem. But all of my choices are in grams of NaOH. So I need to change grams of NaOH into moles using the molar mass, and then I can change moles to kilojoules using the heat of neutralization. So I'm going to need to do a calculation for each of these 4 answer choices. So in reaction 1, we're starting with 50 grams of NaOH. I'm going to convert grams of NaOH into moles, and then I can convert moles into kilojoules. So grams to moles is going to be molar mass, which is 40 for NaOH. And the heat of neutralization for reaction 1 is negative 57.1 kilojoules for every 1 mole of NaOH from the balanced equation. So this gives my answer. I get negative 71.38 kilojoules. I'm going to need to repeat this calculation for all 4 options. So I did all of these calculations the same way. I took grams to moles to kilojoules. And the one that produces the most heat, that gives off the most heat, these are all negative numbers because this reaction is exothermic. The one with the most is option D, which is the 60 grams of NaOH. Question 8, refer to tab 6. A 20-gram sample of glass is heated from 23 to 75 degrees Celsius. How much copper would be needed to make the same temperature change using the same amount of heat? So this is a 2-step problem. First, we're going to find Q for the sample of glass. Then we'll use that value for heat, the specific heat for copper, and the same delta T in order to find the mass of copper, which would give us the same temperature change. So first, I'm going to use Q equals mc delta T to find Q for the glass. So we had 20 grams of glass. The specific heat from tab 6 was 0.840 joules per gram degree Celsius times the temperature change from 75-23. So that's going to be an increase. We do T2 minus T1. So I get Q is 873.6 joules. Now I'm going to use Q equals mc delta T again, but this time I'm solving for M. So I'm going to put in the number we just got for Q. I'm going to put in the specific heat of copper, which is lower than the specific heat of glass, and the same delta T, same temperature change. So here I'm just solving for M, and I get 43.63. So then the best choice is choice A. Question 9, refer to tabs 4 and 6. Which of the following could result in a heat of reaction that is too low? Select all that apply. So there's probably going to be more than one correct answer here. The first choice, the lid does not form a tight seal with the calorimeter. So what that means is that we're going to have heat loss because of that poorly fitting lid. So some of that heat gets lost instead of changing the temperature of the water in the calorimeter. So we end up calculating a heat of reaction that's too low. Option B, there's friction between the stirring stick and the lid. So that's going to release heat into the water. So the temperature change that we get would be too big. So the heat of reaction that we calculate from Q equals mc delta T would be too high. So that choice is not going to give us a heat of reaction that is too low. Next one, ethyl alcohol is accidentally put into the calorimeter instead of water. So ethyl alcohol has a lower specific heat than water. It's about half the specific heat of water. So what this means is that as the reaction occurs, the heat that is released would cause a bigger temperature change. So this would give us, once again, a heat of reaction that is too high. So choice C will not work. D, there is already a small amount of water in the calorimeter before the newly measured water is added. So if we have additional mass in our cup that we haven't accounted for, that means that our number for mass is too small. So if mass is too small, heat is going to be too small because we calculated Q equals mc delta T. So this is also going to give us a heat of reaction that is too low. So choices A and D are the best choices. Question 10, refer to tab 5. How many grams of sodium fluoride would be produced if reaction 6 releases 150 kilojoules of energy? So heat of neutralization is again given in kilojoules per mole. So I can very easily change kilojoules into moles just using the heat of neutralization. But all of my answer choices are in grams. So that means that I'm going to need to convert moles of sodium fluoride into grams, and I can do that using the molar mass. So I'm going to start with our given, which was negative 150 over 1, kilojoules over 1. And then I want to change kilojoules into moles using the heat of neutralization. So I would have to look at the reaction and see how many moles of sodium fluoride and then get the heat of neutralization. Then I'm just going to take the moles of NaF and convert it into grams because all of our answer choices are in grams. So 1 mole of NaF from the balanced equation releases 68.6 kilojoules, and 1 mole of sodium fluoride weighs 42 grams. So this gives us 91.83 grams of sodium fluoride. So the best choice is choice C. Question 11 asks you to refer to tab 6, which gives the specific heats, and then figure out which sample from the graph could be 6.25 grams of silver. So the best way to solve this problem is going to be to choose a value for heat from the graph. So I'm going to pick 2. And then solve for the delta T that we would expect with this value for heat using the specific heat of silver. So whichever line intersects at that coordinate for Q and delta T is the correct answer. So I'm going to pick 2 because my lines all cross energy transferred of 2 at distinct places. So the first one, the red line, which is sample A, crosses at about 1.4 degrees Celsius. Sample B crosses at 2. Sample C crosses at 3. And then sample D crosses at 5. So basically I'm going to plug 2 into Q equals mc delta T along with the mass of silver and the specific heat of silver and solve for delta T. So whenever I do this, I get delta T is 1.333 degrees Celsius. So the line that's closest to that is going to be sample A. So if you put 2 joules of heat into sample A, you get a delta T of about 1.3. So that must be silver. Question 12 asks you to refer to several tabs and describe the heat transfers that occur when doing an experiment to find the heat of neutralization. So this is the calorimeter that was provided. And we can make lots of heat transfers here. We could say that heat is being transferred from the reaction to the water, to the inner vessel, to the airspace, to the outer vessel. But then just in simple terms, we've got the heat changes that cause error, and then we've got the heat changes that we need in order to find the heat of neutralization. So heat is going to be transferred from the reaction to the water to the thermometer. We can use that delta T for the water along with M and C for the water to solve for Q. So if I know delta T of the water and I know how much water I have, I can figure out how much heat is absorbed by the water. The heat that is gained by the water is exactly equal to the heat given off by the reaction, except for places where we have heat loss. So the heat transferring from water to calorimeter to the air eventually, that causes heat loss, which is a source of error. So we'd probably get a heat of reaction that was a little bit too low due to heat loss. We could try to quantify how much heat loss there is. So for example, we can calculate a calorimeter constant. How much heat does the calorimeter absorb whenever you do a reaction inside of it? We can actually quantify that and then get better values for the heat of neutralization.